Hi, I'm Bytes. I work at Akamai on our various performance products, mostly the features that are part of Ion. I also work on browsers, in particular Chromium and WebKit, adding performance features that we need as part of our products. And I'm here today to talk about why the web is inherently slow, which is a very sad thing to say as a web performance freak, but it's the truth. But on the bright side, I'm also going to talk about how can we make it faster despite that fact. So I've been part of this industry for a while now, and when I first started, I was working on a mobile data web optimization proxy, as one does. And my very first task on the job was to build a proprietary network protocol that wasn't unlike what Speedy does. And so a network protocol that is able to send multiple requests and receive multiple responses all at once over a single connection. My second task was to integrate an image compression library into the proxy server. And the image compression library was usually getting very good results, usually reducing the size of images by a factor of 2. And at those days, network bandwidth was a serious issue with the top-notch mobile networks clocking at the cool 33 kilobits per second. But we soon noticed something odd. Even with those awful speeds, cutting the image sizes, cutting the image bytes by a factor of 2 did not give us a factor of 2 performance improvement, unless the image compression was deployed at the same time as the Speedy-like network protocol. And at first, we were kind of baffled by this because it wasn't obvious why that is. If we're cutting down the bytes that we're sending down by a factor of 2, why aren't we seeing a 2x performance improvement? And the reason this was the case is that on the web, the basic equation to calculate how long downloading a site takes, these equations don't really apply. We cannot treat the contents of a site as bytes that we download. The contents of a website are progressively discovered, progressively rendered, and often continue to download beyond the point in which a user considers the site to be loaded. And one of the reasons for the non-linearity that we saw was the impact of latency on the HTTP protocol. The fancy networks of that time delivered only 33 kilobits per second, but they also did that with round-trip times, or RTTs, of 700 milliseconds, making the page loading performance mostly dominated by latency. So HTTP 1.1 is a kind of an odd protocol. It opens multiple connections, at the time 2 connections per host, but only delivers a single request over those open connections. So if we have to download 50 images to a page, that means it will take us 25 RTTs, even if all our images are so small that they can fit into a single packet. And that would take us, with the RTT of 700 milliseconds, that would take us 17.5 seconds to download all those images. So just to illustrate, we would download 2 images at a time, send 2 GET requests in parallel, get the responses for that, then send 2 more, and so on and so forth, until all the different requests were downloaded. But that was a long time ago. And the industry has since moved on from HTTP 1.1 to H2 and other newer protocols, and all those problems are gone, right? Well, we advanced a lot in the last almost 20 years, which makes me feel old. And we have significantly better networks, significantly better protocols such as HTTP2, H2 for short, and quick, improved image formats, and we have significantly faster computers. At the same time, we also have significantly slower ones. And network latency on cellular networks have decreased significantly, but in many cases, physical latency, moving packets from one side of the world to the other one, hasn't changed much. And content on the web has evolved significantly over the last 20 years as well, from simple text-based sites with images and an occasional JavaScript-based form validation. The web has turned into a full-fledged application development framework, and one where you download the entire app every time you want to use it. And as a result, the web is still weird. Our performance bottlenecks are rarely where we think they are. And despite high-speed networks, we still see a lot of slow websites out there. So what I want to discuss today is, first of all, how browsers work, because I believe that in order to figure out how to make something faster, we need to first understand how it works. Then I'll talk about the various web performance issues that we see on the web today, and finally talk about the various solutions to these problems. But first, let's start out with some definitions, because I see a lot of people conflating web and internet out there. Just to clarify, as our friends at Google tell us, the internet is a global computer network providing a variety of information and communication facilities consisting of interconnected networks using standardized communication protocols. The web, however, is a network of fine threads constructed by a spider from, no. The web is a network of interlinked documents identified by their URLs, accessible via the internet. So it's a network of documents, applications, and content delivered over that network of computers. And a browser is a computer program that is used to display that content and navigate the web. So if we'll use a metaphor, the internet is the roads, the web is the interconnected cities on those roads. URLs are the road signs, and the browser is the vehicle we use to get from one location to the next. So how do browsers load web pages? Browsers are built from multiple components that all play a significant part in loading of web pages. The networking layer is fetching the required resources from the web server. The rendering engine interprets those resources and finds more resources to download. The JavaScript engine executes scripts, which often leads to more resources to download. Decoders decode the various media formats into something that can be displayed to the user, and graphics layer paints all of that to the user's screen. So it's a very delicate and complex process. And what happens when the user clicks on a link or type in an address to the URL bar? Well, first of all, the browser is sending out a DNS request and get a DNS response as to where that server is, which takes us one RTT. Another RTT is used to establish a TCP connection, and then two more RTTs for TLS, and only then can the request for the resource go out to the server. And once the server starts sending the response down, this is where we hit TCP slow start, which is a mechanism that on the one hand enables the server to gradually discover the connection's limits and not saturate it and send more data than the connection can handle. At the same time, it also limits the amount of data that we can initially send in that initial RTT when the server is sending down the resource to the browser. once the HTML starts arriving at the browser starts processing that HTML. It tokenizes it and runs it through the preloader in order to find out as soon as possible which resources are actually needed to load. And the reason for that is that a web page is comprised from multiple different file types. We have HTML, CSS, JavaScript, fonts, images, and other media formats, all discovered either by the preloader or by calculating styles and finding the required resources, or by executing JavaScript and finding resources that are explicitly needed. And the browser needs to discover those resources as soon as it possibly can, because some of them are critical to render the page to the user. First of all, the browser needs the HTML in order to construct the DOM, the document object model. Blocking scripts block the parsing of HTML, so block the creation of the DOM until they are fully downloaded and executed. And CSS is required in order to create the CSS object model, which together with the DOM is required to create the render tree, which is required for layout, which is required to paint actual content to the user. So before the user sees anything, we need to download enough of the HTML and all of the blocking CSS and JavaScript. This is what we often refer to as critical resources. When downloading resources, browsers need to decide which resources are more important than others. The basics are described here. So HTML is more important than CSS, more important than JavaScript, which is more important than fonts, which are more important than images. But the actual logic that implementations use is often more complex than that, because blocking scripts at the top of the page are often higher priority than blocking scripts at the bottom of the page. And asynchronous scripts are lower priority than blocking scripts. And viewport images are higher priority than out-of-viewport images. And this entire logic is not really defined anywhere on purpose, and it can vary between different browsers and between browser versions. So browsers play around with those priorities in order to figure out the best set of priorities in order to get maximum performance. So if we look at the resource download dependency tree, the browser starts out with just downloading the HTML. That's the only URL it is aware of. Then it discovers CSS, JavaScript, and images and downloads them as well. CSS and JavaScript can often download other resources, which then can download even more resources. So for example, background images are notorious for being discovered late because the browser has to wait until all the styles are downloaded in order to calculate the overall style and figure out which background images are needed. And fonts are even more complex than that because the browser has to download all the styles as well as enough DOM to find where these fonts are actually used. And if they're not used, they're not really downloaded. OK, so that's bigger than what I thought it would be. So let's go over these problems in detail and see what pain is actually caused. So first of all, we have server-side processing. Then discovery, bloat, out-of-control third parties, as well as client-side processing, which for some reason is bloated, and I hate CSS. Starting off with server-side processing. So traditionally, this was the most important thing to optimize when talking about web performance. Backend speed and time to first byte before starting to send down a response response to a request. Steve Souders did a lot of work on that front and found that in most cases, 80% of the time actually spent to load a page is spent on the front end, not the back end. So the time it takes to send the HTML is only responsible for 20% of the overall page load time, which is important to focus on front-end performance, but at the same time, 20% is nothing to scoff at. So server-side performance is still very much something to be concerned with. And at Akamai, we see median server-side time to first byte between the ad server and the origin at around 450 milliseconds, which is a lot. And the historical advice about server-side performance was to flush early. Basically, not wait for the database calls or other complex processing in order to start sending down the probably static HTML head and let the browser start processing it and fetching some resources. The problem there is that if those database calls or that server-side processing fails, that can impact the entire document. So for example, we can respond with a completely different 404 page versus our normal 200 pages. And it's not trivial to switch the pages on the user when such an error has happened without fully reloading them. And we basically need to bake that logic into our application in some way. So that's tricky. The other second performance issue is discovery, because of the way that browser work that we discussed, many times browsers have to download resources in order to figure out which resources to download in order to figure out which resources to then download. So we have a lot of resources that are loaded at a late phase in the load page, and JavaScript often also loads resources, which can, again, lead to very deep dependency trees that have many layers and contain many nodes. This is a sketch of a dependency tree that I was sketching out on a whiteboard at some afternoon, trying to figure out where things happen, actually on the same site that had this pattern, which you can see the bandwidth pattern here contains many holes. Sorry. So we have very complex dependency trees, and we have trouble filling the bandwidth pipe in many cases. And the reason for those, ideally, we would love to be able to flatten out this dependency tree and tell the browser about all those resources at an earlier phase. But there's inherent tension between that and the way that we humans like to think about things. And we often like to write code in smaller modules. And therefore, we have CSS imports. We have the new ES6 modules because they make it easier for us to think of pieces of our code separately. But at the same time, they make it hard for the browser to figure out what it needs to download. Another problem is bloat, because traditionally we've been building websites for desktop. And also because of network speeds, we were compressing our images to avoid slowly loading images. But as broadband got better, we started compressing our images less and less and added more of them. So moved from 400 kilobytes of images in 2011 to 1.7 megs nowadays of average images per page. And also, as more devices came to market, each with their own viewport dimensions, responsive web design became the only option, the only scalable option to write web pages. But in its most naive version, we just kept sending the same images we needed for our high-end desktop machines to all devices, which consumed a lot of bandwidth and resulted in a lot of bloat. But the problem with bloat is not just bandwidth. The devices, and again, talking about phones mostly, they're not only downloading resources on often flakier networks, but they also need to process them with significantly less CPU power, and they also have less memory to deal with the consequences. So, and other than images, we also have CSS and JavaScript related bloat, where CSS frameworks are great to develop to, but often mean that you're sending unused CSS code to the browser. And JavaScript frameworks and libraries often have a similar impact, where you're sending a lot of code to only use a small part of it, and you're pegging down the mobile CPUs in the process. And finally, third parties, which everyone likes to complain about because it feels good to complain about them. Because by definition, it's someone else that is doing something bad, and you're good. You're taking care of your performance. It's just the third parties that are dragging you down. But when people talk about third-party performance, like the third-party performance problem, they often refer to many different aspects of third-party performance. Some third parties block your rendering and will slow down your website's first paint if they're slow to load. In many cases, those are also causing a front-end single point of failure. So if those scripts fail to download or block for long times, they will effectively DOS your site. Bandwidth contention also often happens because third parties are downloaded over a separate H2 connection, which means they're downloaded from a different server, and their download is not correlated with the first-party resources. So they can slow down your first-party resources even if they're not blocking in and of themselves. Some of them are bad actors that result in downloading excessive amounts of content, which the user doesn't necessarily care about. They could trigger periodic beacons that wake up the user's radio network and drain their battery. They can hijack the user's scroll and touch events in order to keep tabs on what they're doing on the page, which can easily result in janky user experience. And they can basically, when downloading massive amounts of scripts and images, they can easily cause main thread contention, where the browser is mostly executing JavaScript and decodes images for those third parties rather than render your content or react to your users' actions. And probably the hardest part here is to figure out whose third party is it and why are they actually running on your site. Because as developers, you're often adding a tag manager, and then that tag manager brings along its tag friends, which brings along their tag friends, and together all of them have a third party all over your website. And you have very little say in the matter. OK, so if we're all properly depressed because everything is awful and slow, let's move to the more upbeat part of the talk and talk about how we actually solve this and what can we do about it. And basically, how can we make our websites faster despite all this awfulness? Well, for server-side processing, it's hard to give you generic advice on how to speed up your server-side processing. You can probably instrument it and figure out which operations take time and try to optimize them. But at the end of the day, executing complex, scalable applications to create the dynamic HTML pages can take time. And it certainly doesn't help that the default runtime for popular high-level languages such as Python and Ruby is not extremely fast by default. But even if our backend times can be slow, that doesn't mean we can't put this waiting time to good use. And we can do that by using HTTP2 server push, which is a feature of the H2 protocol, which enables us to send down resources before the browser requested them. And basically enables us to put the network connection to good use while we're waiting for the HTML to be generated by the origin server. In other words, we can turn this bandwidth graph into this and use all this idle waiting time before the HTML is sent down in order to send down the CSS and JavaScript, the critical CSS and JavaScript. So here, instead of sending the HTML only after we got it from the server, we can start sending down the CSS and JavaScript. And then when we get the HTML, we can send it down in one go, because a secondary effect of that is that we warmed up the TCP connection. So we passed the slow start phase using the CSS and JavaScript. And when we get the HTML, we can send it down to the browser in a single RTT. So we've talked earlier about discovery and seen that it's a real issue because the browser cannot download the resources that it doesn't know about. So how can we tackle that problem? The first part is to use pre-connect in order to skip the DNS, TCP, and TLS phase, or at least move that phase out of the critical path for any blocking third-party resources. So we can pre-connect to those third-party hosts ahead of time, and then when we actually download the resource, we just download that resource and save 4 RTTs in the process. Another is using H2 push, because we talked about that in the context of server-side processing, but at the same time, it's also helping the browser downloading undiscovered resources to the browser before it discovers, before it realizes that it actually needs them. So we can do that before the HTML even arrived. And a third thing that we can do here is to use preload, which is another recent feature I've been working on, and enables you to tell the browser to kick off a download of a certain resource without defining the exact point where that resource will be used. So you can decouple the resource download from its execution and effectively flatten out the dependency tree by preloading late discovered resources ahead of time. And if we compare preload to push, it has multiple advantages. You can use that on third-party resources, where H2 push is mostly working for first-party resources, or resources that are under the first party's control. Preload also enables you to take the cache state into account, as well as the cookies, so you can you don't need to predict the cache state, and you don't need to avoid pushing, avoid preloading resources that have cookies on them. It can be used in content negotiation scenarios. So for example, it can be used to download WebP images only to browsers that support them by using the accept headers. And on top of that, it has load and error events, so you can build complex JavaScript-based loading logic by using preload. And what's push's biggest advantage? The one we've seen before. It can be used to fill up the idle time before the browser ever received the HTML, which results in significant boost to the time the user first sees content on the screen. Now, push and preload cannot solve all the discoverability problems, because in some cases, your content is truly random, and you actually need to run JavaScript on the client in order to figure out which resources will be needed. But as web developers, we can try to limit that variability and also make sure we push and preload everything that we can predict. And just because Ted here made me explicitly say it, in case it's not obvious, pre-connect and H2 push are already part of the adaptive acceleration behavior that is part of Ion. And we're also looking into automatic preload. Now, other things related to discovery that are being worked on, a recent standard proposal called Early Hints proposes a way to be able to send some headers to the browser before the response is complete. So while we're waiting for the server to send us the HTML, we can start by sending the browser response headers that indicate either pre-connect or preload instructions. So that can be helpful for either third parties or first parties. Priorities are also, for preload, priorities are determined using the as attribute that is part of the preload tag. So we tell the browser that this is a resource of a certain type, and then the browser adjusts the priority accordingly. I'm also working on a different specification called priority hints that will enable us to define explicit priorities for certain resources and change from the default. So we could define important scripts versus unimportant scripts, or important images versus unimportant images. OK, now bloat. What can we do about bloat? What can we do about the fact that we're sending down too much content? Well, the good news here is that bloat is, as web developers, it is in our hands. We just need to send less bytes down the wire. The first and obvious step to do that is better image compression, which is often easier said than done. And while the lossless aspects of image compression are obvious to automate, there are also lossy parts that are significantly harder, because we have to make sure we're compressing the image as much as we can without creating visible artifacts that will degrade the user experience and make our designers angry. So there are multiple open source projects and multiple workflows that you can integrate into your build process, which can help you get better results there. And then there's responsive images, because we talked before about responsive web design resulting in sending high-resolution images to all devices. Well, the web performance community realized that this is a huge issue, formed the responsive images community group a few years back, and after a long while and numerous arguments with various people, we managed to convince browser vendors that we need a way to specify multiple images for browsers to download based on the device, dimensions, design, and the browser's environment. So we came up with the picture element, as well as the source set and sizes attributes on the image element, and specified them and shipped them in browsers. And nowadays, all modern browsers support them. So those tools, alongside with client hints, which is the content negotiation equivalent of them, enable us to, they're basically tools that help us manage image bloat on the web and reduce it to a minimum by sending the images each device needs and not sending more image data than that. And there's also much progress on bloat on the web in terms of better compression algorithms, better image formats, etc. And again, the main hurdle to adoption is often managing all the variants and getting the image compression just right. And just in case it's not obvious, Image Manager is really good at handling all that complexity for you. More in the front of bloat, new compression algorithms enable us to shrink text files even further. So we have Zopfli and Brotli, which enable better compression for text files by putting in more CPU. Zopfli is gzip compliant, and Brotli is a brand new format, which gives us 20 to 30% better compression for our text files. And again, just in case you don't know, Resource Optimizer, the latest addition to adaptive acceleration, performs automatic Brotli and Zopfli compression for all your static cacheable resources. And if you prefer to serve Brotli from origin, this is also supported and properly cached, like different variants are properly cached. We talked a little bit about dependencies, small modules and their discovery issues, but small modules also tend to compress poorly. And traditionally, we bundled resources together in order to avoid the negative impact of multiple requests, but we also got significantly better compression ratios from that bundling. And with H2, we don't really need to bundle in order to avoid the number of requests, but the compression is still an issue. So on that front, there's a proposal I'm co-authoring to enable shared compression dictionaries as part of the H2 protocol, which will solve this issue and enable significantly better compression for small CSS and JavaScript files. And now to third parties, a few things you can do to ease the pain. One is pre-connect and preload that we already discussed, which enable you to speed up render blocking third parties. Service Worker, which is an extremely powerful browser feature that enables you to run a network proxy, a JavaScript network proxy in your browser, enables you to get back control over third parties and know what they are, put SPOF protection in place, and otherwise defer or terminate them in ways that weren't practical before. And another recent API that can help you be aware of the impact, runtime impact of third-party scripts is the long task API. And Nick Jansma will talk about a lot of the work that he's been doing with that API on Friday morning. So be sure to catch that, even if it's after the party. It's extremely cool stuff, which enable you to pinpoint and assign blame to third parties that are causing user jank. And again, Ted's face, Script Manager, new feature going into beta, is doing a lot of that in order to make sure that you have control over your third parties. Another proposal that is highly promising for third parties is the certificate frame, which will enable us to coalesce different third parties, different Akamai's third parties on the same connection as the first party. So that will enable us to avoid bandwidth contention with third parties because everything will be managed on a single connection. And it will also help us get rid of the connection establishment that these third parties currently incur. And the last bit is client-side processing. And for that, I don't have much advice other than the obvious advice of sending less JavaScript and CSS. There are best practices around the build step that enable us to only send the critical CSS down, and but they tend to be hard to configure and put in place. For JavaScript, there are various build step solutions, for example, Webpack, that using tree shaking and other algorithms make sure that you don't send down JavaScript you don't need. But again, it's not always something you can use, and it highly depends on your workflow and how you write your code. And there's also server-side rendering, which may or may not be applicable and should be carefully applied to make sure you're not serving a frozen version of your site that is not responsive until JavaScript actually comes in. So unfortunately, I don't have a TED face here for this particular category, but it's definitely an area we're putting a lot of thought into. So takeaways. Latency still dominates web performance. Even though many years have passed, we still have discoverability issues which are dominated by latency. There are multiple reasons why your content can be slow, and each performance problem has to be investigated on its own. On the bright note, we can improve things. We can flatten our dependency trees. We can use the server think time and all those things that we discussed. And finally, Ion is pretty awesome. Thank you.